Lesson 8.2, Finite Arithmetic Series. In this video, we will use summation notation to rewrite finite series and calculate given sums. Why was the obtuse angle upset? Always upset. Because it's never right. Vocabulary. Series is the sum of the terms in a given sequence. Arithmetic series is the sum of an arithmetic sequence. Finite series is the sum of a finite number of terms. Catching on to the pattern here. Infinite series is the sum of an infinite number of terms. So basically, if you see the word series, it just means the sum of. Notation for the summation. So summation notation is noted by the Greek letter sigma, which is, in this case, is the capital sigma. The number on top of it is the upper bound of the summation, where the n is. The number down below here, the I here, is the index of a summation. Other things that you could see there would be I, sometimes J, K. I think there's a couple others, but those are the three ones that I've seen commonly used in that spot. Yep. All right. What it equals is the lower bound, okay, of the summation. So in other words, the beginning of the summation, and the top is the end of the summation, like the last term. The a sub I is an index and indicated variable representing each successive term in the series. Okay, so that's where your arithmetic sequence or geometric sequence goes. And then the other form of it, when it's written out, it means that you have a1 plus a2 plus a3 plus a sub n minus 1 plus a sub n. You're just adding up every number in the sequence. Okay, that's what it implies. But instead of writing out a sequence of 1,000 numbers, we can write it in the summation notation form. Use summation notation to rewrite each finite series, then calculate the given sum. Alright, so if we look at number one starts at 5, ends at 21, and if we count, we have 1, 2, 3, 4, we have 5 terms altogether. So we're going to start with our sigma. On the bottom is I equals 1. We're going to start with the first term, and it goes to 5 because there are 5 terms. The next part is the part in here, and we have to find that. So we're going to find that by finding the arithmetic sequence. So I'm going to move this down here out of the way. So we're adding 4 each time. So a sub 1 is equal to 5. D is equal to 4. So we have a sub n is equal to 5 plus 4 times n minus 1. Now I can use this, or I can simplify this, right? Distribute the 4. So So we get 5 plus 4n minus 4, and so a sub n is equal to 4n plus 1, because 5 minus 4 is 1. So I can either have 5 plus 4 times I minus 1, or I could use I equals 1 for I plus 1. Both of those are the same. Okay, so whichever you choose, it works just fine. But it's going to be one of those two. And then it says, then calculate the sum. So the sum they're talking about is this here. They want us to find s sub 3. So we're really saying 5 plus 9 plus 13, which is going to be 27. So what I'd like you to do is try number 2 right now, and then check and see how you did when you're done. Okay, so hopefully you noticed that we're multiplying by 2 every time. The first term is 3, so you can see that I found my geometric sequence first. Okay, you can rewrite this geometric sequence so that it doesn't have n minus 1, but just an n in the exponent, so that puts it in exponential form by the sequence that you see there. You don't have to do that. And so then you either have this sigma with I equals 1 on the bottom and 7 on top, and then 3 times 2 to the I minus 1, or you have 3 halves times 2 to the I. And then it said to find the sum of the first 6 terms. So we went ahead and add up the first 6 terms and get 189. And that's how we use summation notation to rewrite finite series.